Is the cosmology we have known for the last 100 years incorrect? A boy was born on July 17, 1894, in Charleroi, Belgium, who showed keen interest in science and mathematics. Despite the challenges posed by World War I, where he served as an artillery officer, he pursued higher education in physics and astronomy. After the war, he studied at the Catholic University of Leuven and later earned a PhD from the Massachusetts Institute of Technology, MIT. In 1927, he proposed a theory of what would later become known as the Big Bang theory. He suggested that the universe originated from a primeval atom, a singularity that expanded and evolved into the vast cosmos we observe today. This groundbreaking idea laid the foundation for modern cosmology, challenging the prevailing notion of a static universe. He is known as Georges Lemaître. The journey of unraveling the universe's secrets has been anything but linear. With each new breakthrough, such as the revelation that the Earth is not the center of the universe or the discovery of black holes, humanity has been forced to reconsider long-held beliefs. The very nature of space, time, and even reality itself has been altered by groundbreaking events, such as Einstein's theory of relativity and the James Webb Telescope's stunning revelations about the vastness of the cosmos. Even our perception of time and the fundamental laws that govern existence have been revolutionized. Today, we delve into some of the most groundbreaking events in history that have completely reshaped our understanding of the universe. From the moment early astronomers began observing the stars to the latest discoveries in astrophysics, our view of the cosmos has undergone remarkable transformations. Over time, advancements in technology, the evolution of scientific thought, and the courage of questioning conventional wisdom have continually challenged and refined our most fundamental ideas about the universe. What we once believed to be absolute truths have been questioned, adjusted, and in many cases, completely overturned by new discoveries. As we continue to venture deeper into the unknown, we face new and profound questions. What is the foundation principle on which the universe is working? Will humanity ever fully comprehend the mysteries of quantum particles? Could there be life out there waiting to be found? And perhaps most intriguingly, what might the next great discovery be? One that changes everything we thought we knew. As we keep exploring, the quest for understanding is far from over, and the mysteries ahead may be even more astonishing than we ever imagined. So what are these most crucial discoveries that led us to re-image how the universe works? You're watching Space 9, unveiling the mysteries of the cosmos, your gateway to the universe. Pioneer research debunking mysterious energy. In 1998, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed something unexpected. Type Ia supernovae, a particular kind of stellar explosion involving a white dwarf, were not appearing as bright as they should have. Not only were they dimmer than expected, but their redshifts indicated that they were much farther away than previously predicted. Even when taking into account the constant acceleration theory, which suggests that an opposing gravitational force could be influencing this phenomenon, the data still did not align with expectations. This led to an alternative hypothesis. The rate of expansion of the universe is not just constant, but actually increasing over time. To illustrate this, imagine standing at the center of the universe with two objects, one on your left at 20 miles and another on your right at 10 miles. According to the expansion theory, after some time, the left object should move farther away by the same factor as the right object. However, the 1998 supernova observations raised serious doubts about this assumption. They suggested that the rate of acceleration itself increases with distance. In other words, the farther away an object is, the faster it moves away from us. This realization led to an even bigger question. What is causing this acceleration? To explain this mystery, Michael Turner coined the term dark energy. But does dark energy really exist, or is there a counter theory? In 2007, theoretical physicist David Wiltshire proposed an alternative explanation, the timescape cosmology model. The Big Bang theory and dark energy models have traditionally relied on the lambda cold dark matter model, which assumes that the universe is homogeneous and isotropic. This means that, on a large scale, the universe should appear uniform in all directions. The cosmic microwave background radiation, one of the most well-known pieces of evidence supporting this model, seems to confirm this idea. However, as observational technology has advanced, new findings have begun to challenge this assumption. Dark energy, by its very nature, does not interact with electromagnetic radiation, only with gravity. This makes it incredibly difficult to observe, and even today, we are nowhere near fully understanding it. Further observations have continued to cast doubt on our conventional cosmological models. For example, the European Space Agency's Euclid satellite has identified numerous regions where the expansion rate of the universe differs significantly from expected values. These inconsistencies suggest that the universe is not as homogeneous as once thought. It does not expand at the same rate everywhere. So, does this mean that everything we believed in the 1990s was wrong? Not exactly. The earlier observations were not incorrect, but they may have been misinterpreted. As per timescape cosmology model, what we perceive as dark energy might actually be an effect of gravity. According to this model, in regions dense with galaxies, gravity is stronger, causing time to slow down, a phenomenon predicted by Einstein's general relativity. Conversely, in the vast emptiness of cosmic voids, time flows more freely. In other words, the more matter present, the stronger the gravitational influence and the greater the time dilation. This means that when we observe objects in high matter environments, such as supernovae, their redshift appears much greater, making them seem as though they are moving away faster than objects in lower density regions. So why do high matter objects appear to be accelerating away? The key lies in how we perceive time in different gravitational environments. Objects in denser regions experience time differently, leading to an increased redshift that distorts our interpretation of their movement. This, according to the timescape cosmology model, was the illusion that misled researchers in 1998. To reconcile their findings, scientists introduced the concept of dark energy. But according to this model, there is no need for such a mysterious force. Instead, the observed discrepancies can be explained by variations in gravitational influence across different cosmic structures. New challenges from the James Webb Telescope further complicating the picture. Recent observations from the James Webb Space Telescope have detected the oldest known star, with a redshift indicating that it predates even the Big Bang according to our current models. If we consider the timescape cosmology model, this apparent paradox can be explained. During the early universe, this star may have been surrounded by an immense amount of matter, causing extreme gravitational time dilation. As a result, the star has effectively experienced time differently from other objects, making it appear much older than it actually is. This suggests that the star did in fact form after the Big Bang, but our observations are skewed due to gravitational distortions. Rethinking the foundations of cosmology. These new findings challenge us to rethink our foundational theories. If the timescape cosmology model proves to be correct, we may need to rewrite our entire understanding of astrophysics. The idea that the universe is homogeneous underpins many principles of modern cosmology, and if this assumption is incorrect, it could upend much of what we thought we knew. The pursuit of understanding the cosmos is far from over. With each new observation, we are forced to refine, challenge, or even discard long-standing theories. Whether dark energy is real or merely an illusion caused by gravity remains an open question. But one thing is clear: the universe is far more complex and mysterious than we ever imagined. Quantum mechanics versus classical physics. Quantum mechanics is one of the most groundbreaking scientific revolutions in history, fundamentally altering our understanding of nature at its most basic level. This theory emerged in response to the limitations of classical physics, which, despite its success in explaining macroscopic phenomena, failed to account for numerous observations at the atomic and subatomic scales. This script explores the origins of quantum mechanics, its foundational principles, and how it contradicts classical physics. Classical physics, rooted in the works of Isaac Newton and James Clerk Maxwell, provided an excellent framework for understanding motion, forces, and electromagnetism. Newtonian mechanics and Maxwell's equations successfully described planetary motion, engineering mechanics, and electromagnetic waves. However, by the late 19th century, several experimental observations began to challenge classical theories such as blackbody radiation and the ultraviolet catastrophe. Classical physics predicted that a perfect blackbody should emit infinite energy at short wavelengths, ultraviolet region, a divergence known as the ultraviolet catastrophe. This contradiction highlighted the inadequacy of classical wave theory in describing electromagnetic radiation. Photoelectric effect experiments showed that light could eject electrons from metal surfaces, but classical wave theory could not explain why only certain frequencies of light could trigger this effect, regardless of intensity. Atomic spectra shows crucial gaps in classical physics, as it could not explain why atoms emitted light in discrete spectral lines instead of a continuous spectrum. These problems indicated that a new theoretical framework was necessary to understand the microscopic world. The resolution of these anomalies came from several key discoveries in the early 20th century, like Max Planck's quantization of energy in 1900 that solved the blackbody radiation problem. Planck proposed that energy is quantized, meaning it is emitted or absorbed in discrete packets called quanta. He introduced the famous equation E equals h nu, where h is Planck's constant and nu is the frequency of radiation. Einstein's explanation of the photoelectric effect in 1905 that extended Planck's idea and proposed that light itself is quantized into particles called photons. He showed that the energy of these photons depended on their frequency, successfully explaining the photoelectric effect and earning him the Nobel Prize in 1921. Bohr's atomic model in 1913 applied quantization to atomic structure, proposing that electrons occupy discrete energy levels and transition between them by absorbing or emitting quanta of energy. De Broglie's wave-particle duality in 1924 suggested that particles such as electrons exhibit both particle-like and wave-like behavior, fundamentally altering our understanding of matter. Heisenberg's uncertainty principle in 1927 formulated the uncertainty principle, stating that one cannot simultaneously determine both the position and momentum of a particle with absolute precision. Schrödinger's wave equation in 1926 developed a mathematical framework describing particles as wave functions, leading to the probabilistic interpretation of quantum mechanics. Born's probability interpretation in 1926 introduced the statistical interpretation of the wave function, asserting that the square of the wave function gives the probability of finding a particle in a given state. But how quantum mechanics contradicts classical physics? Classical physics is deterministic, meaning that the future behavior of a system can be predicted exactly if initial conditions are known. Quantum mechanics, however, is inherently probabilistic, meaning that we can only predict the likelihood of an event occurring. In classical physics, waves and particles are distinct entities. Quantum mechanics unifies them, showing that electrons and photons exhibit both wave-like and particle-like properties, depending on how they are observed. Unlike classical objects, quantum particles can exist in multiple states simultaneously until measured. This is famously illustrated by Schrödinger's cat thought experiment. Classical physics assumes locality, meaning objects only influence their immediate surroundings. Quantum mechanics demonstrates entanglement, where two particles remain instantaneously connected regardless of distance, defying classical intuitions about space and time. Unlike classical mechanics, where energy is continuous, quantum mechanics states that energy levels are discrete, explaining atomic stability and spectral lines. Similarly, Where a particle must overcome a potential barrier in classical physics, quantum mechanics allows particles to pass through barriers due to their wave nature, explaining phenomena such as nuclear fusion in the Sun. Also, quantum mechanics describes how superpositions collapse into classical states through interactions with the environment, bridging the gap between quantum and classical realms. Beyond theoretical implications, quantum mechanics has paved the way for numerous technological breakthroughs. The development of semiconductor devices, including transistors, has revolutionized modern electronics, enabling computers and communication technologies. Quantum mechanics governs the behavior of light amplification in lasers, which are essential in medicine, communications, and industrial applications. Unlike classical computers that use bits, quantum computers leverage qubits to perform calculations exponentially faster for certain problems. Even MRI technology, based on quantum spin properties, has transformed medical diagnostics. Also, secure communication systems leverage quantum principles such as entanglement and uncertainty to prevent eavesdropping. So quantum mechanics revolutionize science, providing profound insights into the fundamental nature of reality. It not only resolved inconsistencies in classical physics, but also led to technological advancements such as semiconductors, lasers, and quantum computing. Despite its counterintuitive nature, quantum mechanics remains one of the most experimentally verified theories, continuously shaping our understanding of the universe. As research progresses, it may unlock even deeper mysteries about the fundamental fabric of existence, potentially leading to breakthroughs in quantum gravity and the unification of physics. Exoplanets, discoveries. The discovery of exoplanets, planets that orbit stars outside our solar system, has had a profound impact on how we understand the universe, planetary formation, and the potential for extraterrestrial life. Before the 1990s, the notion of planets existing beyond our solar system was largely speculative. It was based on theoretical models and circumstantial evidence that suggested their presence, but no concrete proof existed. The first breakthrough came in 1992, when astronomers Alexander Wolszczan and Dale Frail made the first confirmed detection of exoplanets orbiting a pulsar, PSRB 1257+12. This monumental finding shattered the prevailing assumption that planets could only form around main sequence stars like our Sun, opening up entirely new frontiers in astrophysics. Pulsars, previously thought to be lifeless remnants of massive stars, were now understood to have planetary systems, suggesting that planetary formation could occur in much more extreme environments than previously imagined. The field truly gained momentum in 1995, when Michel Mayor and Didier Queloz discovered 51 Pegasi b, a gas giant in orbit around a Sun-like star. This discovery, which earned them the Nobel Prize in Physics in 2019, marked the first confirmed detection of an exoplanet orbiting a main sequence star. This achievement proved that planetary systems were far more diverse than our solar system, and that stars similar to the Sun could host planets as well. 51 Pegasi b, often referred to as a hot Jupiter, was a particularly unexpected discovery. It was a massive gas giant that orbited extremely close to its host star, completing an orbit in just over 4 days. This discovery upended traditional models of planetary formation, which had suggested that gas giants, like Jupiter and Saturn, could only form in the outer reaches of a star system, far from the heat of their star. The existence of such a planet close to its star indicated that planetary migration, where planets move inward or outward due to gravitational interactions, was a common occurrence, and that planetary systems could be much more varied than previously believed. As observational techniques advanced, particularly with the launch of space-based telescopes like NASA's Kepler Space Telescope, the discovery of exoplanets exploded. Launched in 2009, Kepler revolutionized our understanding of planetary systems by using the transit method. This method detects exoplanets by measuring the small dip in a star's brightness as a planet passes in front of it. Kepler's observations allowed scientists to detect thousands of exoplanets, many of which were unlike anything previously imagined. the telescope's data revealed a diverse array of planetary types, from Earth-sized rocky planets to gas giants, to planets that fall into new categories that had not been considered before. Among these discoveries were super-Earths, planets that are larger than Earth but smaller than Neptune, and mini-Neptunes, a class of planets that were previously unknown to science. These findings significantly expanded the range of known planet types, showing that planets could form in a wider variety of conditions than scientists had previously thought. One of the most significant impacts of exoplanet discoveries has been the realization that planetary systems are not only common in the galaxy, but also incredibly diverse. Before the discovery of exoplanets, many scientists believed that planetary systems were relatively rare and that most planets would have characteristics similar to those of our own solar system. However, the exoplanet research has shown that planetary systems are far more varied than anyone expected. Some systems contain multiple planets packed closely together, while others have planets in highly elliptical orbits, and some even feature planets that orbit two stars instead of just one. In addition to these previously unknown configurations, the discovery of rogue planets, planets that do not orbit any star but instead drift freely through space, has further expanded our understanding of the diverse environments in which planets can exist. These revelations have forced scientists to revise traditional models of planetary formation. Early models of planetary formation were based on our solar system, which has a clear structure. Rocky planets like Earth, Venus, and Mars are located closer to the Sun, while gas giants like Jupiter and Saturn are farther out. However, exoplanet research has revealed that planetary migration is common, with planets moving inward or outward over time, due to gravitational interactions between planets and their host stars. This process has led to many planetary systems that do not follow the pattern of our solar system. In some systems, gas giants are located much closer to their star than our own Jupiter, while smaller rocky planets are located farther out. The discovery of such systems has led to new theories of planetary formation that take into account migration, star interactions, and the complexity of planetary evolution. Perhaps one of the most exciting aspects of exoplanet research is the search for planets that may be capable of supporting life. Over the past 2 decades, astronomers have discovered a number of exoplanets located in the habitable zone of their star, the region where conditions might allow liquid water to exist on the planet's surface. These discoveries have reignited humanity's curiosity about the possibility of extraterrestrial life. Some of the most promising candidates for supporting life include Proxima Centauri b, a planet orbiting the closest star to our solar system, and the TRAPPIST-1 system, which features 7 Earth-sized planets, 3 of which lie in the habitable zone. These discoveries have significantly raised the probability that life-supporting planets exist elsewhere in the universe, suggesting that Earth may not be unique in its ability to support life. In addition to reshaping our understanding of planetary formation and habitability, exoplanet research has also driven significant advancements in technology. The development of high-precision spectrographs, improvements in direct imaging techniques, and the planned launch of space telescopes like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope are expected to provide even more detailed insights into exoplanet atmospheres. Spectrographs are now capable of detecting the chemical composition of an exoplanet's atmosphere, and scientists are working on methods to detect potential biosignatures, gases like oxygen, methane, and carbon dioxide that might indicate the presence of life. The ability to study exoplanet atmospheres in such detail could bring us closer to answering one of humanity's oldest questions. Are we alone in the universe? The discovery of exoplanets has also led to a fundamental shift in how we think about our place in the cosmos. In the past, many people believed that planetary systems like our own solar system were unique, but statistical analyses of exoplanet populations have shown that planets vastly outnumber stars in the galaxy. This challenges the idea that our solar system is special or rare, and suggests that Earth may be just one of countless worlds in the Milky Way, alone capable of supporting life. This realization has profound implications for fields like astrobiology, as well as for philosophy and our understanding of humanity's place in the universe. If planets are so common, the chances of finding extraterrestrial life may be far greater than we once thought. In summary, the discovery of exoplanets has radically transformed our understanding of the universe. What began as a speculative field of study has blossomed into one of the most exciting and dynamic areas of modern astronomy, providing insights into planetary systems, habitability, and even the potential for life elsewhere in the universe. From revealing new and unexpected types of planets to reshaping our understanding of planetary formation, exoplanet research has opened up vast new avenues of inquiry. As technology continues to improve and new missions, such as the James Webb Space Telescope, come online, the coming decades promise to bring even more groundbreaking discoveries that could change our understanding of the universe and our place within it. First black hole observation. The first image of a black hole represents one of the most monumental milestones in the field of astrophysics. It is a discovery that transcended the boundaries of imagination, showing a direct visual representation of an object that had previously only been theorized through complex mathematical equations and indirect observations. The image of the black hole, located at the center of the galaxy M87, was not only a technical achievement, but it also reshaped our understanding of the universe, confirming many theoretical predictions while opening new doors for future research. The concept of black holes has its origins in the late 18th century, with John Michel and Pierre-Simon Laplace, who independently theorized about dark stars, objects so massive and dense that not even light could escape their gravitational pull. However, it wasn't until Albert Einstein's general theory of relativity in 1915 that the true nature of black holes was understood. According to Einstein, massive objects warp the fabric of space-time, creating deep gravitational wells. These wells could, theoretically, become so deep and narrow that nothing, neither matter nor light, could escape once it passed a certain point, known as the event horizon. While the theory of general relativity predicted the existence of black holes, they remained invisible to direct observation. For many years, black holes were enigmatic objects in the cosmos, detectable only by their influence on nearby stars or the light they bent through gravitational lensing. In the decades following Einstein's work, scientists developed mathematical models that further refined the concept of black holes, with key contributions from physicists such as Karl Schwarzschild, who formulated the solution to Einstein's equations that described the geometry of spacetime around a non-rotating black hole, and Stephen Hawking, who introduced the idea of black hole radiation. Despite these advancements, the notion of imaging a black hole seemed almost impossible. The gravitational pull of a black hole is so intense that it traps everything within it, including light. This makes it extraordinarily difficult to detect directly, and for many years, black holes were considered to be purely theoretical objects. The breakthrough came from a collective effort involving the Event Horizon Telescope, EHT collaboration, an international team of scientists and astronomers who united their efforts to push the boundaries of what was considered achievable in the realm of observational astronomy. The EHT collaboration, which was founded in 2012, set out to capture the first ever image of a black hole. Their approach was to combine data from multiple radio telescopes located across the globe, effectively creating a planet-sized virtual telescope. This technique, known as Very Long Baseline Interferometry, VLBI, allowed them to observe the event horizon of a black hole in unprecedented detail. However, the technical challenges were immense. The object they aimed to capture was located 55 million light-years away, and the size of the black hole itself was roughly 6.5 billion times the mass of the Sun. Furthermore, the image they sought to capture was only about the size of a grapefruit seen from across the United States, making the task of obtaining such a resolution a monumental challenge. The breakthrough came in April 2019 when the EHT collaboration released the first ever image of a black hole located at the center of the galaxy M87. a massive elliptical galaxy in the Virgo cluster. This image showed a glowing ring of light surrounding a dark central region, the shadow of the black hole. The image was a stunning visual confirmation of the presence of a supermassive black hole at the center of M87. The glow around the black hole is not emitted by the black hole itself, as light cannot escape from within the event horizon, but rather by the hot, ionized gas and matter being pulled toward the black hole and heating up as it spirals inward in a process known as accretion. The image of M87's black hole provided a number of groundbreaking insights into the nature of black holes and their role in the cosmos. First and foremost, it confirmed a central prediction of Einstein's theory of general relativity, that black holes, despite being invisible, should cast a shadow due to the bending of light by their immense gravitational pull. This shadow, which corresponds to the event horizon of the black hole, is the boundary beyond which not even light can escape. The 2019 image also had profound implications for our understanding of the universe in broader terms. For one, it provided direct visual evidence of the existence of supermassive black holes at the centers of galaxies. Prior to this discovery, the idea of supermassive black holes had been largely based on indirect evidence, such as the motion of stars near galactic centers and the behavior of gas clouds. The image of the M87 black hole solidified the role of supermassive black holes as central engines driving the formation and evolution of galaxies. Furthermore, the image challenged and enhanced our understanding of general relativity. The black hole in M87, being so massive, offered a unique opportunity to test the limits of Einstein's theory in a region of space where gravity is at its most extreme. While the image itself did not directly challenge general relativity, it sparked new questions and areas of exploration. For example, the sharpness and clarity of the image raised the possibility that future observations could probe the behavior of space-time even closer to the event horizon. These observations could offer insights into the nature of quantum gravity, a still elusive theory that seeks to reconcile general relativity with quantum mechanics. The discovery of the first black hole image also brought attention to the mysteries of accretion disks, the rotating masses of gas and dust that swirl around black holes. The glowing ring observed in the M87 image was a result of the intense gravitational and magnetic fields in the regions surrounding the black hole. Scientists are now studying how the material behaves in such extreme conditions, and whether it can help explain phenomena such as relativistic jets, powerful streams of particles that are often ejected from the poles of black holes. In terms of technological advancements, the successful imaging of a black hole marked a leap forward in the field of observational astronomy. The EHT's achievement relied on cutting-edge techniques in radio interferometry, high-performance computing, and image processing. The data collected by the array of telescopes was so vast and complex that it required advanced algorithms to stitch the information together into a single coherent image. This breakthrough is a testament to the power of global scientific collaboration and technological innovation. In the years since the first image was released, the EHT collaboration has continued to refine its methods, with hopes to capture even more detailed images of black holes, including those located in our own galaxy. One of the most exciting possibilities is the study of the supermassive black hole at the center of our Milky Way galaxy, known as Sagittarius A star. This black hole, while smaller than M87's, is much closer to Earth, making it an ideal candidate for further study. The release of the first image of a black hole in 2019 also had profound cultural and philosophical implications. For centuries, humanity has looked to the stars with wonder, pondering the nature of the universe and our place within it. The image of a black hole serves as a stark reminder of the vastness and complexity of the cosmos, as well as the limits of human understanding. It also highlights the unyielding nature of scientific inquiry, the willingness to push the boundaries of knowledge, no matter how daunting the challenges may seem. Many scientists think that this first image of a black hole in 2019 was a groundbreaking achievement in the history of science. It not only provided direct visual evidence of an object once thought to be invisible, but also confirmed key predictions of general relativity and opened new avenues for exploring the most mysterious and extreme regions of the universe. The implications of this discovery continue to unfold, with ongoing research promising to reshape our understanding of black holes, gravity, and the very fabric of space-time itself. In conclusion, groundbreaking discoveries have continuously expanded our understanding of the universe, revealing its vastness and complexity. From debunking dark energy to exoplanets, these revelations have reshaped our view of space, time, and entire cosmology. The discovery of the timescape cosmology model confirmed predictions about the fabric of space-time, while the detection of exoplanets opened up new possibilities for life beyond Earth. The advent of the James Webb Telescope provided stunning images, pushing the boundaries of our cosmic knowledge. The exploration of dark energy continues to challenge scientists, highlighting how much remains unknown. These breakthroughs serve as milestones in our ongoing quest to understand the cosmos. They remind us of the importance of curiosity and the pursuit of knowledge in unraveling the mysteries of the universe. The future holds even more potential for transformative discoveries that will continue to redefine our place in the cosmos. Each step forward brings us closer to understanding the fundamental nature of existence. Ultimately, these discoveries fuel our collective desire to explore, learn, and marvel at the universe's endless wonders. Hope you enjoyed this topic. Please let us know which of these intrigued you the most. If you liked our video and want to join us on this journey of space exploration, please like and subscribe to our channel. Thanks for watching.